Hello everyone, this is De Zhong, a PhD student from Structural Computer Interaction Laboratory at UCLA. Today I will discuss automated stability testing of elastic rod with helical centerlines using a robotic system. This figure shows a robotic is manipulating an elastic rod to become different helical shapes. Not all helical shapes are stable. When elastic instability occurs, the rod will buckle to a non-helical shape. When an elastic rod with a helical centerline buckles is one of the most fundamental problems in mechanics. In this presentation, I will explain why the problem is essential and how to solve it with robotics. First, let's learn about the background information. Now we see the buckling process of a pipe in the ocean. Under some specific boundary conditions, the pipe will have a large deformation in a relatively short time, and the pipe's functionality will be influenced a lot. Therefore, buckling analysis is always significant in mechanical design. We will use the buckling process of a twisted ribbon, as shown in this video, as example to show how to do the buckling analysis. First, we need to decide the boundary conditions. Then, a combination of analysis method and experiment validation is used to get the buckling information, when the structure buckles and how it buckles. However, because the boundary conditions usually have several degrees of freedoms to be precisely controlled, it is challenging to use traditional experimental platforms like optical platforms to do experiments. This work introduced robots as the basis of a novel experimental platform to study mechanics, since it's automated and accurate. The ability to control multiple degrees of freedom can make it satisfy requirements of boundary conditions. Based on that, robots can be used to construct automated experimental platforms to study mechanics. In this project, the rod with a helical centerline is the system we want to study. Helical shapes has two important geometric characteristics, radius a and pitch 2 pi b. Combine these two parameters, we can derive the curvature kappa and torsion tau. There is also one additional characteristic of the system, twisting moment omega. For this system, we only have these three characteristics. We will figure out when the rod with helical centerline buckles. The analysis tool we use here is discrete elastic rod, a fast simulator with sufficient accuracy. In DER, we can capture the internal energies and forces based on the defined discrete node and frames. The internal forces balance with external forces to formulate the Garvin equation. With Garvin equation, we can do the numerical analysis for the system. Here, we propose a scheme to find out when the system buckles. We explore the buckling point in the parameter space of three independent characteristics. Each exploration will start from the original point of the space and move along a straight line. This plot shows the change of the shape during the manipulation. X-axis is the exploring distance along the searching direction, the red ray in the top figure, and the y-axis is the difference between the rod's shape and the desired helical shapes. We can find the rod will become helical confix initially. When exploration achieves a buckling point, the slash line, a certain change will happen. Based on this scheme, we designed the experimental setup shown there. The motor and the robot will collaborate to give the desired boundary conditions. The camera will track the attached markers to get the rod's confix. We introduce an intermediate frame at the manipulated end during manipulation, which has zero twist via the material frame at the clamp end. Therefore, the robot's manipulator will add the intermediate frame, which only controls the curvature kappa and torsion tau. The external motor will only control omega, the twisting moment. With our contents stated before, we combine simulation and robotics to construct an automated platform for studying the system. Here are the results. We attach a demo here. In top figure, all point on the blue surface are buckling points. Since the surface is anti-symmetric, we can only explore the region where torsion tau is larger than 0. We can find good agreement between the simulation data and experimental data. We can conclude that the robot can work as an automated platform to test the onset of buckling stability in structure.